Good day and welcome back to the second part of our discussion on the chain rule applied to functions of several variables. In the previous video we looked at version 1 of the chain rule, where these kind of composition functions only depended upon a single variable, whereas we generalize that idea for version 2. So to get started, let's think about the functions we have in terms of a diagram once again. We start off with z, or a function f, which depends upon two variables, x and y. But now we're going to go ahead and let those individual variables, x and y, depend upon two variables themselves, both s and t. So in terms of the function z, it is a function of both s and t. So instead of being ordinary derivatives as they were in version 1, these are in fact partial derivatives. And how we get these partial derivatives is we follow down the branches of our tree diagram. To find dv ds, we look for all of the instances that correspond to an s in the bottom row, and then we have to go down both of those, in this case, corresponding branches. And each of these limbs, in a sense, will correspond to a partial derivative. So dz ds is going to be dz dx, dx dt, and these are partials. And that's going to correspond to going down the first branch, dz dx, multiplied by dx ds. So note my typo here, that should have been a dx ds. And then when we jump to that next branch, we put a plus sign, and similarly, we would now need to go down it, dz dy, dy ds, and those are partials. So dz dy, the partial of y with respect to s. And similarly, for dz dt, you can note the spots where t ends up in that bottom row and go down those corresponding branches. So we would have dz dx, dx dt, plus dz dy, dy dt, where each of these are partial derivatives. And two observations I want to note. The first, just verbally, I will always strongly encourage you to draw a tree diagram, and we will in fact always do that as well. And the second observation I want to make, similar to our observation following version 1 of the chain rule, is that this also works just fine for functions of more than two variables. So let's explore several examples dealing with this version 2 of the chain rule. For the first example, what we would like to do is for the function f, depending upon x, y, z, and t, we'll call this w for convenience, with those variables x, y, z, and t all depending upon u and v, write down the chain rule for the partial of w with respect to v. The first thing I'm going to do is try to encode all this information into a tree diagram, make it look hopefully as simple as possible. We have w, which depends upon four variables, x, y, z, and t. Each of those four variables, in turn, depend upon two other variables, u and v. And in order to determine the partial of w with respect to v, we locate the four v's in the bottom row of our tree diagram, and we need to go down each of the branches that culminates in that desired v. And note in this example, we're not asked to necessarily compute anything. We're really only asked to write the chain rule formula. So we have kind of one step remaining here. Using our tree diagram to aid us, the partial of w with respect to v, going down that first branch, is the partial of w with respect to x times the partial of x with respect to v. And then we have similar terms corresponding to each of those branches that we go down. And what we end up with, these four terms added together, gives us the desired chain rule formula. And hopefully this is a good starting point, kind of illustrating how we could apply the chain rule formula to more than just two variables. But let's make this more concrete and actually have some functions that we're going to deal with. So in the final example of this video, I'm telling you that u is a function that depends upon x, y, and z, and each of the x, y, and z individually depend upon r, s, and t. Whew. And what we'd like to find is the partial of u with respect to s. So similar to the previous example, I'm going to go ahead and just write down the chain rule. And I'm going to do so first by drawing a tree diagram. We have u depends upon x, y, and z, and each of the x, y, and z depend upon r, s, and t. So something you should be able to tell me now by inspection is when you write down the formula for the partial of u with respect to s, how many terms will it contain? And if you said 3, I agree. One term for each time the s appears in the bottom row of this tree diagram. Applying the second version of the chain rule, the partial of u with respect to s is the partial of u with respect to x times the partial of x with respect to s, plus two more corresponding terms for both y and z. And in terms of finding du ds, this really leaves us, several partials that we need to compute. And then once we compute all those partials and combine things together, we will think about substituting in those values. So let's just go ahead and work our way from left to right and substitute in what these quantities are. The partial derivative of u with respect to x, 4x cubed y, plus 0, because remember, with respect to x, y squared z cubed is simply a constant. And this is multiplied by the partial of x with respect to s. So r e to the t. And really, at least at this point, this just feels like an exercise in calculating a whole bunch of partial derivatives. The partial of u with respect to y, we treat the x and the z's as constants. So x to the fourth plus 2yz cubed multiplied by dy ds. That would be 2rs e to the minus t. Plus the partial of u with respect to z, which is simply 2y, times the partial of z with respect to s, r squared sine of t. And this completes the differentiation portion of the problem. And no, we do need to, in a sense, somehow substitute what is x, what is y, what is z, to get this all in terms of r's, s's, and t's. But note, since we're evaluating this at specific values, r equals 2, s equals 1, t equals 0, we don't necessarily need a formula involving all r, s's, and t's. We could instead substitute those values in above to figure out what values x, y, and z will take when r is 2, s is 1, t is 0. And I think that just cuts down a bit on the writing. So note, when r is equal to 2, s is equal to 1, and t is equal to 0, one can quickly compute x is going to be 2, y is also going to be 2, and because sine of 0 is 0, z would be 0. So in terms of evaluating this, note this is equivalent to also including x is 2, y is 2, z is 0. So working left to right and substituting these values in, 4 times 2 cubed times 2 times r e to the t. So 2e to the 0 plus 2 to the 4th plus 2 times 0 cubed, we like to see that, multiplied by 2rs e to the minus t. So 2 times 1 e to the 0 plus 2 times y, so 2 times 2 multiplied by r squared sine of t. So note, sine of 0 is 0, so that term is also going to vanish. So 2 squared sine of 0. And we should simplify this maybe just a smidge. Note the third term we've added in is entirely 0. Also note this middle term, a piece of it, cancels. And if you were to go ahead and simplify this all out, and please feel free to plug it into a calculator if that helps, you would get back 192. Now this completes our discussion of the second version of the chain rule, and what really remains is to go through some additional practice. And instead of trying to throw one more example into this video, I'm going to break it up into a third and probably a smidge shorter of a video. So stay tuned and take care.